Okay. Can everybody hear me? Yeah. What?
Yes.
Okay. Sweet. Thank you. Yeah, so welcome, EE225E, lecture a lot. Woo! Yeah, a lot of lectures of a lot of water has flown as a streamed through the Sacramento while we started this class. So by now you again you know quite a bit about MR, although you don't know everything, but if you actually open a paper, you might be able to pretty easily read through and understand at least what people are talking when they talk about different techniques. Let's see. Ekin, do we have any announcements?
There's a homework due tonight, and then the next one will be posted as well. That's it. Yeah, and the signups for the next lab will be posted soon as well.
Well, actually, there is something I want to talk about. I want to talk about the project proposals. So if you only have one reference in your project proposal saying that you would research your, thing and or review a topic, and the only reference that you have is a review article, that doesn't count. Because if you just take an article that already reviews something and you just summarize what that article, that doesn't count as a project. So all of you that have put only a single reference in a project proposal, this is not what I expect. Okay, so you have to do a little bit more work in describing what exactly you'll be describing if you want to do a project that wasn't suggested. Please go and update that as soon as possible. And what we're going to do is we're going to have some time to schedule 15 minutes meetings with each group, such that and we're going to start them on a weekly basis. So I'll have some time available, and Ekin will make some time available, and we'll have you sign up. And so we kind of have some idea of how your progress in the project is going. And the idea would be to not just give you necessarily a final score, but also to see that there is constant progress. Because if you're going to cram everything to the last minute, it doesn't also count to me as a great project. So that's it. The results of the midterm will be posted. I think we have to grade it first, so it will take some time. But we'll once we're done grading it, then we'll post the results. Okay. Any questions? The other thing, actually, the other thing about projects, if you, in terms of deliverables, so yes, there's going to be a presentation, but if your project is just a literature review of a topic, then in addition to that literature review, I will ask you to write a Wikipedia entry or update the Wikipedia entry on the topic that you researched. So at least it will benefit not just me or you, but may benefit actually more people. And if you actually take a look at some of the MR references, some of the previous classes that incarnation of this class have updated some of these. I don't know, maybe you'll have to look at the history because they might have been deleted. Who knows what Wikipedia does, but at least it's going to be somewhere for people to see. Okay. Any more questions? You have a lot of questions today, so I mean, might as well spend some time answering all of them. Fascinating. Well, at least I heard yes from Sam. Thanks, Sam. All right. I guess we'll start. Yes. Just to make it interesting, we'll do a quiz today in class. Okay. So towards the end of the class, we'll do a small quiz. It's really not meant to be graded, although we might, but it's really just for us to understand, to see if you're actually picking up whatever we're trying to tell you. All right. So where were we? Oh yes, where were we? We were talking about sequences and contrast, and we looked and we did some analysis on the case where first TR, the time repetition was much longer in the T1, so everything is, goes back into the initial state, and then you start again with magnetization M0. M0 points at MZ. Then we went and looked at what happens when your time repetition is smaller or the order of T1 relaxation. Hence, the magnetization is not fully recovered in the MZ, albeit it's still longer than T2, which means that there is no transverse magnetizations left. And there we analyzed a few cases. We analyzed the situation of saturation recovery, where we excite with a 90 and we wait, and then excite again with a 90, and the TR, the time repetition will be then affecting your T1 weighting and how much you emphasize, different values of T1 based on the TR. There's really no other knobs there. It's just what is the TR. Okay. The other knob that we had was the echo time. In particular, what will be then the weighting that's added when you change the echo time? Quiz number 1.
Would be T2 star.
T2 star. Twinkle, twinkle. Yeah. Now we know what it is. Yes, T2 star. And if you do saturation recovery with the spin echo, what would then be, what would TE would do? The echo time?
It would be T2.
Who said that?
Me.
Okay, thanks, Amit. Yes, it would be T2. Right, so with a spin echo, it would be T2, absolutely. Okay, then we also looked at the situation where we want to enhance our T1 sensitivity, and we looked at the case of an inversion recovery, where we first apply an inversion followed by a I guess a saturation recovery, right? So there's an inversion, saturation, recovery, inversion, saturation, recovery. And we analyzed that case, and we saw that when you apply an inversion, you have more sensitivity to T1 and more degrees of freedom. Particularly, you can null a particular T1 species based on the inversion time and the repetition time and the T1 of that particular tissue. So it's possible then to null its particular tissue, which it's tremendous. Think about it. I showed you some examples in the brain where we null CSF, and then you could see very nicely, actually, let me pick up this example. On the left, this is a T2 flare. Actually, yeah. This is a T2 flare. And the only reason that you can see this, this inflammation over here is because the CSF is being nulled, hence fluid that still is within the tissue, so it doesn't behave exactly like free water, but it still has a very long T2, but not as much as free water, has a very strong signal, so you can see it in the brain. And if you actually don't do this, yes, this is what you see. And this is compared with nulling the CSF, and you see how, you know, this huge difference in terms of the ability to see this particular lesion. Okay, so really big effect to be able to null. And the other tissue that often is nulled is fat. So fat, I showed you some example, I think even in lecture 1, where there was edema in the bone. And so that was obstructed by the fat in the bone. And if you saturate fat, then you could see the edema in the bone. Similarly in the breast, often we would like to inject contrast agents. So there's a dynamic contrast enhancement studies in the breast where you inject, you know, these type of contrast agent. This is a gadolinium contrast agent. Particularly this one is Gadovist. It shortens the T1, so you inject it into the person's body, and you want to see how it's being well, at least it's dynamic within different tissues. Of course, cancer has a lot. You know, the cancerous tissue would build and create blood vessels to feed the tumor. And so, and often these are done very fast. And so the blood vessels in cancerous tissues is very leaky. So the gadolinium would often leak into the tumor. And so it will enhance. Its T1 will shorten, and you will be able to see it much brighter on T1 weighted images. However, if you have fat also has short T1, and so that obscures your ability to actually see. And so fat suppression is very common for dynamic breast imaging. And one of the issues there is if you want to do very good fat suppression, you also have to have very good field inhomogeneity, because you want to invert just fat and null it completely. And if there is field inhomogeneity, that's sometimes you might do that to the water tissue. So you have to be very careful about how this is being done. Okay. All right. The last thing that we analyzed last lecture was the case of arbitrary I guess excitation recovery, basically just arbitrary flip angle that you know, theta, 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 theta. And in that case, we derived a maximum signal, which is the Ernst angle that depends on the TR and T1 that maximize the signal. Of course, it not necessarily maximizes the contrast, but they maximize the signal that comes out of this particular T1 that you optimize for. Okay, any questions? Laura, any questions? No questions. All right. Okay, so let's move on and look at now the more complicated case. And the more complicated case, when the TR is shorter than T1, but it's also shorter than T2. So what it means that there's an MXY component that persists before the next RF. Okay, before the next RF being applied, there's an MXY component that persists, and that could be an issue, because, for example, while you excite some magnetization, you know, things could have happened to that MXY magnetization before the next RF. For example, it may have shifted in phase due to off resonance, right? It could, you know, there's many things that can happen to it during this time. And since it persists, it will be affected by the RF excitation. So the RF excitation will not just excite new magnetization that has recovered during this time, but it will also change the flip angle of the magnetization that's already in the transverse plane. And that will either add, subtract from the current signal being, from the next signal that being excited. So there's, and that can persist over many, many cycles of excitations. In particular, some of the time repetition that I'm talking about can be at the order of maybe 2 milliseconds. Okay, so you repeat every 2 milliseconds. There's really not much time for the magnetization to decay, not in the transverse and not to recover much in the longitudinal direction. And the question, what happens there? Right, this is a very interesting problem. Now the question is like, why even bother do that? That's quiz number 2.
To save time.
Who said that?
Anita.
Anita. So sweet of you. So, okay, so let me play you a sound. I'll just try to imitate a sound of an MRI with a 1 second time repetition. Okay. Click, 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 click. That's how it sounds. Okay. Now imagine that you have 512 phasing codes. You know, you're going to hear this click for, I don't know how long. Well, actually, it's pretty easy. It's 512 seconds. You're going to hear this click, and then only at the end, you'll get an image. Now, 512 seconds, that's actually a lot. That's almost 9 minutes or something. I mean, it's like, it's pretty long time. So that's a problem, right? Now, if I play it for, let's say, half a second, it'll be click, 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 click. Oh, faster, right? You know how it sounds when you have about 2 milliseconds time repetition? And that's, for example, there's a sequence called S of P. If you want to make a single image, it sounds like this. That's it, done. That's pretty good, right? Like, that's much faster than click, 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 right? So you can finish an image with, you know, very, very short amount of time, because you are able to excite and do phasing coding and all of that in orders of, you know, a few milliseconds, and you repeat that very quickly and you're done. Okay. So remember that cutting the TR by a factor of 2 often, not always, will speed up your acquisition significantly. So of course, there was a lot of work that's been done early in the 80s in order to do fast imaging, because really that was how it was MRI. It's like it was click, click, very inefficient. People wanted to come up with new ways of creating contrast, or maybe generating T1 contrast, but without the need to wait so long. Okay. One case that really makes a big difference is dynamic contrast enhancement again, where you have a very short T1 due to this nice contrast agent that you inject. But then, you know, if you have to wait so long, then it doesn't make any sense. Okay. All right. So the question is how to do it. All right. Well, this is what we're going to do now, is we're going to look at these, what we call steady state or short TR steady state images. And there's different variations about them. Now remember the surprise part. Well, this is the TR, and then at the end of the TR, sometimes we'll have a surprise, and that surprise will make a huge difference on the image contrast. And the question is like, why and how? Okay, and again, this is going to be a lot of hand waving today and a lot of videos. Oh, did you make popcorn? Like I saw Anita with the banana, but I mean that's also a healthy choice, rather than just eat, you know, pure carbohydrates. No, a drink over there. That's nice. Anybody else? I have some coffee. Oh, blueberry blaze, nice. I actually have a cookie also. It's an almond cookie. Fantastic. All right, ready? Okay. The first one among those steady state sequences is the one that we called balanced steady state free precession, or balanced SFP. Other names: True FISP, Fiesta, Balanced FFE, or BASG. That also, but I've never seen this, to be honest. But Brian Hargraves swears that that's also a name. The idea for this sequence, actually, there's a paper. The original paper is from '56. It comes from NMR. That describes the situation of what happens when you apply RF pulses continuously at a very, very short repetition. So the question is, what is the present? What is the surprise that we have at the end of the sequence for balanced SFP? And the answer is nothing. You basically do nothing at the end. Okay, you do nothing at the end, which is quite interesting. But the things that you have to notice here that we have what we called balanced gradient. This is why it's called balanced SFP. If you look and you try to integrate over the gradient area, right? Integrate over the gradient area within a TR, and you notice that the area integrates to 0. Right? The area here, whatever in the phasing code, for example, you play a particular phasing code. Well, what you do here, you actually play it the other way. In this case, you have a readout, and often we stop here, right, and have a flat line. But no, with balanced SFP, you also put a post rewinder or a rewinder at the end of the readout, such that the area sums to 0. Now, what happens in this case is that the only thing that is really persistent from TR to TR is the RF. But all the effect of the gradients is being canceled at the end of the TR. So whatever the spins have done, like rotated here, rotated there, rotated this, because of the phasing code, they all go back to the same place that they were originally after the RF. Okay? So from an analysis point of view, we can completely ignore the gradients in order to understand what the spins are doing. The spins pretty much, except for, of course, the slice selection, don't really see the gradients. It's completely transparent to them because they're balanced. Okay, so that is the key for balanced SFP. Okay, all right. Do you hear that? That's the beautiful sound of balanced SFP. Okay, now let me actually show you the dynamics of what happens to the spins. So if you notice, the spins are chopped. Chopped means that we apply a series of a flip angle. In this particular flip angle is 60, followed by minus 60, 60, minus 60, 60, minus 60. And it's slice selective, means that we're only going to excite the slice, and hence we have a gradient here. But you know what? It doesn't really matter if it's slice selective. We, just for the purpose of the analysis, we can just ignore this at all, the gradients, because they're completely refocused, so they're really not affecting anything. They're not producing any phase. Okay, so just look at the magnetization of 60 and minus 60. And what we're going to look at is what happens. What is the dynamic that these spins see? I mean, of course, they're being knocked. 60, minus 60, 60, minus 60, 60, minus 60. Now, if you think about it, let's say there's no relaxation, there's no off resonance, then obviously the dynamic would have been very simple. You knock 60, you get some 60 degrees, and then the next DR, you put it back, in the MZ. And then 60, and then you put it back, right? And of course, it doesn't make a huge sense because, one time you'll get a signal, the other time you put it back, you get no signal whatsoever. You put the 60, you get signal, you don't get signal. So what's the point, right? Well, the point is that, of course, we have relaxation. We have T2 relaxation that's going on, and there's also T1 recovery. And there has to be some steady state that's going to evolve, in a sense that every time the magnetization will come back to the same state such that you'll get exactly the same thing. If you don't, then you either get no signal whatsoever, because if it's not going to end up with a certain steady state, then you get no signal whatsoever. So I guess the steady state would be 0, or otherwise it will be something else. And the question is, what is the steady state? So let's just look at the case where you have on-resonance spins. On-resonance spins will, remember, will be excited, and then they'll exhibit some T2 decay and some T1 recovery. And then they'll be excited to the other way, right? Minus 60. And then they'll exhibit some T2 decay, some T1 recovery, and then they'll be excited again with plus 60. And then, so the T1, T2 decay and T1 recovery kind of need to compensate, some of this, back and forth that's going on. And eventually you end up basically being in one state like here, that you'll, do have a little bit decay, a little bit recovery, and then flip to the other side. A little bit decay, a little bit recovery, and then flip to the other side. Okay, so let's see actually how this evolves. All right, ready? Here's a spin, 60, minus 60, 60, minus 60, 60, minus 60. But every time you notice there's a little bit of decay, a little bit, so the magnetization kind of shifts a little bit, but eventually it will get to a point where when you do minus 60, it ends up with a certain angle. And then when you do plus 60, you will get up again to the same angle, and so on and so forth. So you get to something that is consistent. The beauty of this is that there's always a signal. There's always MXY component. Look at the shadow. The shadow of the arrow represents the transverse component. There's always a transverse component, right? That is not a trivial thing to have, right? It's not a trivial thing to have, because usually, when we excite, right, like we have some T2 decay, and like our magnetization before assumed to be dead in the transverse plane, so that has been killed. And now you only rely on T1 recovery for the signal to rise again, so you could excite it. In this case, you preserve some of the magnetization that's been excited, and you reuse it in the next DR, back and forth. You always reuse it. And so there is some decay that happening, but the steady state is actually ends up with a very, very strong signal. I mean, strong. It's about turns out to be about 15% sometimes. So 15% constant. You can run this for days and you'll get a constant, like you do a repetition of, 2 milliseconds repetition, and you get a constant signal that's coming out of those pins that is about 15%. That's huge. It's a huge signal.
Can you say what you mean by 15%? 15%
If you-
of what?
Of the total magnetization that you have. So this is, this was the original magnetization. Yeah, M0. And then now the transverse component is about 15% of that.
Okay.
Something like that. But it's constant 15%. Every TR, you get 15%. Think about it. I mean, it's crazy. It's a lot. It's a lot to do. I mean, to keep. And you can scan like this for hours and hours and nothing, it's just like, it's going to be like this all the time. Now, here's the trick though. Here's what happens though. What happens when you start to have off resonance? Okay, what would be the dynamic? You excite, right? But then the magnetization starts rotating. But the angle that you apply the minus RF is exactly the same angle. So then you start seeing kind of a more complicated effect. Okay, that's going on. So let's see what happens when you have a quarter of a cycle precession during the TR. Now, what does it mean, a quarter of a cycle? Well, that depends on what the TR is and what is the off resonance, right? It's a factor of both. Right? It could be a very short TR and you have to have a very large off resonance to create a quarter of a cycle. Right? Or you could have a long TR and very little off resonance. Okay, so let's see what is the dynamic. Yeah, actually something I didn't mention is what is actually the amount of magnetization here. Well, it's not T1, it's not T2, it's kind of a mix of both, right? It's actually a very complicated mix of both T1 and T2. And people have kind of derived it and they say, what, the rule of thumb would be kind of a T2 over T1. That's the rule of thumb, okay? So the maximum you get when T2 is equal to T1, if you have something non-isotropic, so T2 is much less than T1, then you'll get a lower signal. Okay, but it's a mix of T1 and T2. All right, let's see what happens when you have off resonance. And actually, don't look at this one, just look at this one. Okay, this is what happens when you have a quarter of a cycle. You excite and then it wanders. You excite the other way and it wanders. You excite and then it wanders quarter, right? And so on and so forth. But then after a while, you start seeing, oh, there is actually a pattern here. Again, it converges into a steady state in which the magnetization kind of traverses and wanders. It's excite to here and then it wanders to here. And then flips to the other side, and then to here. And then basically just go this way, right? Spend some time over here, flips to here, spend some time over here, flips to here, spend some time over here, flips to here, spend some more time. Okay, but it ends up with a steady state of this kind of, it's not a circle, but it's, if you look from above, there is a ring here, and then there's another one over here, and then this kind of flips to the other side. So from above, it kind of looks like that. Okay, so there is a steady state, and there actually a good amount of signal that's left. So even with a quarter cycle of precession, we have a pretty interesting, pretty good amount of magnetization left. So it's useful for our quarter. Now, the question is, what happens when you have half a cycle of precession? Half a cycle of precession is the magnetization, whenever it's being excited, it actually rotates to the other side and being excited again, and then rotates to the other side and being excited again. So it's kind of doesn't go back and forth. It's kind of like it's just being knocked all over the place, just knocked all over the place. And it spends so much time in the transverse plane back and forth, that the T2 relaxation basically kills it. And there's really no opportunity for T1 recovery because it's always rotating. It's all kind of always rotating around. And so you will have zero signal for half a cycle of precession. So good signal on resonance, good signal on quarter, anywhere from on resonance all the way to quarter. But as you reach half a cycle of precession, boom, no signal at all. So it's very sensitive to off resonance. Okay. So effectively, that basically, you have to limit the amount of precession not to have half a cycle. Like you don't want to have half a cycle of precession. Okay, you don't want to get there. Now, that of course depends on your off resonance. And so that effectively, if you have a certain off resonance within your image, that would limit, how long your repetition time can be in order to avoid half a cycle. You really have to go really fast when you have off resonance in order to avoid this half a cycle. So you have to have very, very fast repetition. You cannot have longer repetition. So always short TR. And if you have a short TR, well, that also limits your resolution because, in order to be able to do image high resolution, you have to have enough room to play a readout gradient such that you can traverse K-space, and that takes a certain amount of time. And if you don't have that time, then that limits the resolution that you can actually achieve. So if you look actually at the magnitude response versus frequency, if this is on resonance, this is on resonance, that's 0 off resonance frequency. If we move at 1 over TR hertz, does that make sense? 1 over TR hertz? What's the units of TR? Time. 1 over time, it's hertz. So it's fine, yeah. So 1 over TR of hertz, if we move, we get no signal. If we move the other way, 1 over TR, then we get also 0. Okay, but as long as we keep the off resonance within this band over here, then we should get good amount of signal all the time. Okay, so here's an example actually here. Here, this is the knee image using balanced SFP. And do you see here this kind of area over here that is nulled? Yeah, that's an example of a null that, because of violation of this 1 over TR, like there's enough off resonance over here such that the tissue over here is being nulled. And this is an abdominal scan, and the abdomen is very hard to control off resonance because of a lot of air tissue interface in the bowel. So look at the liver. You see this dark band that appears in the liver. This dark band that appears in the liver is due to this SFP banding artifact, what it's called. And there's another band over here, and then there's another band over here, another band over here. And that depends on the TR. If I would have increased the TR and make the TR longer, you could almost trace the field inhomogeneity looking at those contours of zeros. Like you'll be able to actually kind of almost see the field map with the contours. It's actually lovely to look at. Okay. So that is actually a big deal because SFP is used a lot in the heart. And if you have a lot of off resonance there, then that can create these banding effects. So that's the issue with balanced SFP. But it's very, very fast. So you do repetitions of about 2 to 5 milliseconds. You actually get excellent image contrast in certain situation. And it actually also compensates for flow. So if you have moving spins, turns out that the phase that they accumulate because of the of flowing actually cancels with this type of acquisition. But the beauty about it is that free water often have a very strong signal. Blood has a very, very strong signal in balanced SFP. Myocardium in the heart, actually the muscle tissue, has a much lower signal. So the contrast in balanced SFP between the blood and the myocardium is large, and the signal is very, very high. So you can kind of see very nicely you could very nicely then create contours and segment those images and be able to extract other parameters like ejection fraction in the heart and things like this. It's very, very popular sequence for imaging the heart because of its speed and the contrast that it achieves. It's a beautiful sequence, balanced SFP. Okay. All right. Okay. So that was balanced SFP. Now I didn't show you an equation, but the equations are actually quite complicated, and it's but you can look at, of course, there's several papers that derive all of these. Now the problem is that we have the sensitivity to off resonance, and the question is, can we remove the sensitivity to off resonance, not have this banding effects? Okay, and still have very, very fast time repetition. So the question is, I mean, the reason that there is this off resonance effect is because the magnetization in MXY persists, right? It persists, and and then it can have a different phase because of off resonance, and then I get all these cancellations. So the question is, can I add something here at the end that will spoil the transverse magnetization? Will kill it, effectively kill it, right? And this sequence is called gradient echo for some reason. It's also called FFE. It's called FISP as opposed to true FISP. It's called FISP. It's called GRASS, GRE, fast, field echo, and so on and so forth. And there, the present that we have at the end is a crusher, a gradient lobe that is not balanced. So the magnetization that being excited will see this gradient, and that gradient will create basically a distribution of phases within a single voxel that hopefully will cancel, such that you don't get that banding that you got in SFP, and that would maybe remove. Basically, we're introducing here what off resonance would have done. Right? The fact that I'm putting a gradient, I'm creating off resonance throughout my entire volume, but the gradients actually usually will put a few cycles of phase within a single voxel. So it'll create a lot of off resonance within a single voxel that will probably dominate the natural off resonance. And our hope is that you don't get that sensitivity and will actually do something. And so the question is, like, what is the spin distribution across a slice, across a single voxel within the slice? Let's see what happens. Okay, let's see, I excite, and then what the gradient does, it spreads all those spins in a cone. So within a single voxel, throughout the slice, because it's only applied in GZ, you will get now the spread. And the signal that you're going to get at the end, after that crusher, you see that all the signal cancels. And so you can kind of model this as if there's only now an mz component and there's no mxy component, because the mxy component, all of them will cancel each other. Does that make sense? Let me show you again. Let's burn it and keep the thing. And now I excite, and there you go. And then you end up with effectively now the magnetization being effectively pointing in MZ. And the hope that it will stay this way. What do you think? Will it stay this way? I mean, if it was this the case, if this was the case, and the magnetization would effectively be MZ, then now we're back into the saturation, like the, you know, kind of like a saturation recovery type of sequence, or with a smaller maybe flip angle, not the 90, but something else. So we can get back to T1 weighting, just regular T1 weighting without T2 weighting. Yes? No. The answer is no, that's not the case. Unfortunately, that's not the case, because a complicated thing starts to happen. That was the first repetition. Okay, so the first DR, okay, things look like that. That's the first DR. Now you've got this cone. What happens in the next DR? Well, the next DR, that cone is going to flip. And then spins will start moving in a very interesting situation. So I'm going to show you this. Ready your popcorn. I'm going to eat my cookie now, and let's watch the video. Ready? Oh my God. Oh, look at that spin. Oh, hey, Laura, you're going to see this. Come over here. Oh, look at that. Come on. Isn't that amazing? Take a look, Laura. Oh, right? All right, fine. Go. Just to go. Look what happens. Here's actually a very interesting that happens. You've got all these isochromats, and now they start kind of going back and forth. Some of these isochromats have no signal whatsoever, right? They're very little. Some of them are pretty big. Effectively, though, if you think about it, each one of, like, at every position along the slice, it's like you have different off resonance. And so each one of those pieces of the slice exhibits SSFP, but with a different off resonance. And the signal that we are going to get is the average of all of these. And this is the average of all of them. Some will have no signal, some will have a lot of signal, but they will average out. So you kind of get like a mean signal of balanced SFP across all possible off resonances. But the behavior, I don't know if you noticed, almost looks like a spin echo. Because, you know, magnetization, you know, the thing starts fanning and spreading, but then it flips the other way and then it focuses. And then you flip it the other way, and then it spans again, but then you flip it again and then it focuses. So it almost behaves like a spin echo. Even though we have a gradient here, there's no spin echo whatsoever, like we're not applying a 180. But the steady state gives you almost an effect of a spin echo. I'll have to play it again because it's so wonderful. Okay, no, it takes time to that steady state to evolve. But as it starts evolving, look, you know, spin starts fanning out, but oh, every time during the middle of the echo, At the TE, they focus, 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 focus. It's kind of like a spin echo. Now, the behavior, of course, is also complicated. And it's a mixture of T1 and T2s because it's an average of all these off resonances. So the result is, no, you don't kill the transverse magnetization. It's actually being preserved. And it's really just an average of balanced SFP. Within a voxel, you've got all this behavior of balanced SFP, but within the pixel. And then your signal is being averaged across them. Now, because the signal is being averaged across, then you're going to get a lower signal than balanced SFP. Because balanced SFP will give you a high signal. But now you've got all these lower ones, so it's going to give you a lower signal. But no dark bands. You remove the dark bands. It's pretty consistent throughout everywhere. But as it turns out also that the contrast is being a little bit also compromised because of that. Okay, so here's an example of cardiac imaging with gradient spoiled that I showed you right now, and with balanced SFP. Balanced SFP will have this banding over here, but very large contrast between the myocardium and the blood. This is the blood, this is the myocardium. Look at the strong signal between them. But look what happens here. I mean, the contrast is, it's kind of like you basically put it in a washing machine and the colors have faded, right? It's also sensitive to flow. Do you see the flow effects? Much more significant than flow effects here. You almost see kind of a swirling thing here because when there's flow during the gradients, then it's kind of chaotic. Each part that sees the gradient doesn't see the gradient, sees more gradient, sees different gradients, so you get this effect. So so it's very interesting contrast, but there's no dark bands. You see, there's no dark bands over here. By the way, this is a spiral acquisition. So all the artifacts that you see, the swirling over here, is artifacts because of spiral imaging. And because, yeah. Any questions? So we gained something, no banding. We lost something, less contrast, less signal. Okay. So again, with MRI, when do you use this one? Well, it depends, right? If banding is a real issue, then you want to spoil it. If it's not an issue, then you can use it. Okay. But then people, okay, so even when putting the gradients really doesn't kill, it doesn't really create pure T1 contrast. It's still a mix of T1 and T2s. The question is, can you create a pure T1 contrast with a very, very short ER such that the magnetization, the transfer magnetization still persists, but we want to kill it somehow, but it's very, very hard. I told you that in MR, the magnetization is not very strong. It's, it's a few ppms, right? 6 ppm, 7 ppm. It's very little. So it's very, you don't create much magnetization, but it's very little. It's very hard to get rid of it too. So once it is, it's really hard to get rid of it, right? Because it always comes back. So that's an issue. So the question is how to do a pure T1 contrast with short TR. And there, what we really want to achieve is a fast 3D T1 weighted imaging. Because with 3D, the problem with 3D, of course, that we had in the past is that if we have to wait a lot of repetitions, then we can't really scan the whole 3D. Like we have to do multi-slice and all that kind of stuff. But if we want to excite the entire volume and do very, very short TR, and we want T1 weighted contrast because we want to inject this, the problem when we inject this, if we use SFP or we use gradient echo, the T1 and T2 are shortened, but in the similar way. And so you don't get a very good enhancement. but we want to only make it depend on T1, not on T2. So, hey, you're back. Thanks. We want to make it only on T1. So how do we do it? It's not easy. Well, there's a couple of papers, one by Jens Fromm from 87, the other one by Yuval Tsur in 91. Both very interesting characters, I have to say. Both of them are quite grumpy. I don't know why. Maybe if you worked on this in this area for a very long time, you know, really requires a lot of analysis. So both of them are quite grumpy. Anyway, this sequence is called SPGR, Flash, T1FFE, RF spoils fast. There's actually many names for this. Jens Fromm called it Flash. And so on Siemens system, for example, it's called Flash. On GE systems, it will call SPGR. RF spoiled gradient echo. So what we need to do is kind of somehow to zero out MXY at the end of the TR. How do we reset MXY? We tried with a gradient that worked for the first TR, but didn't work for the rest. So how do we make sure that whatever we excited doesn't really come back and refocuses nicely as like we saw with the gradient echo? The trick is to actually also what's called spoil the RF. Don't look at the videos. I'm going to play them again. The trick is to play the RF. So instead of applying 60, minus 60, 60, minus 60, you increment the phase of the RF with a quadratic phase. And often you increment it with 117 degrees. Ask me why. People have looked at it, did the analysis, and that's the closest one to being a pure T1 at the end. There's a beautiful description of this in the Bernstein book, a handbook of MRI post sequences, if you're interested. But basically, you always increment it. Now, when you increment that phase, every TR, you increment that phase, then it actually never repeats. 117 never repeats itself. So you always get a different phase, a different phase, a different phase, every RF. And so what happens is that it's almost random. It's almost random. So the new flip angle that you apply is random with respect to the rest. And so if you have any magnetization left from the previous TR, it will have kind of a random phase. And basically all the phases, all the signals from the previous TRs will effectively cancel. And only the new magnetization that you're actually exciting right now will have the right signal, like will actually generate the signal. That's the idea. Okay. So what you do is both RF spoiling as well as gradient spoiling. Okay, these are the surprises, this one, and also increment the RF. Now, how does it look? Well, what I'm going to show you is two distributions. One is the real distribution, and the other one is the effective one when you try to average the whole thing. So the real distribution, you see, it's like spread out in a cone, and then it spreads out in like this weird kind of thing. And then now it's like really complicated, really gets complicated. And now if you actually try to sum all those phases, well, they end up canceling, and the actual effective distribution is pretty much as if you're exciting and then it's being killed, exciting and being killed, exciting and being killed. But the real distribution is that you have a lot of spins that are at like random orientation, so they actually cancel in each other's signal. Okay, look at the yarn ball here of mess. You know, that changes all the time, but it just cancels. So the effective one is this. Does that make sense? Okay. Now the issue is that of course it's going to have low SNR because you're only relying on T1 recovery through a very short TR. short time repetition, there's not much time for magnetization. So if you do this type of sequence with a time repetition of 2-3 milliseconds, how much magnetization can recover during that time with T1 of 800 milliseconds? Not much. So most of the tissue will be black. What tissue will be bright? For example, this can shorten the T1 to be very, very short, like 150 millisecond, 100, even less than that, right? So then this tissue that has actually gadolinium or contrast agent will become much brighter compared to the background. So the background would be very dark, and you can do maybe angiography that way, because all the tissue will be dark except the blood vessels. Okay, that's very common. Dynamic contrast enhancement, that's another one. And of course, fat will still be bright. Don't forget, because fat is a very short T1 too. Okay. Here's just two examples. This is SPGR before contrast. You see that very little contrast here. It's like hard to see. SNR is very low. SNR is very low. Whatever, like this is the bladder, for example, you know, very, very low signal. And once you inject contrast, then you start seeing, oh, wow, you know, the blood vessels and all the tissue edges and all that stuff, whatever absorbs the contrast becomes very, very bright. Okay. Look at the blood vessels here in the liver, for example. You start seeing them. Here they're dark. Okay. Here's an example of enhancement over time with contrast enhancement. So this is repeated every 6 seconds. It's repeated 6 second breath holds, and their images are 10 seconds apart. Okay, 32 slices, and this is how it looks. Oh, contrast, and look at how the contrasts have changed. You inject. So the first thing that you see is the aorta being very bright. Let me do it again. You see the aorta being really bright first. And after that, it goes to the veins and the rest of the tissue. And these are the kidneys that will absorb the contrast at the end. These are the kidneys. Let's look at it one more time. Okay. So this type of sequences allows you to do very fast temporal acquisitions with very high sensitivity to very short T1s.
Hey, Mickey.
Okay. Yeah.
Why does it only go to one kidney?
It's a good question. Maybe that's a problem. There is a little bit here, but it's not as good, right? So it might be an issue with the kidney. I wouldn't actually give gadolinium to somebody that has problems with the kidneys. But I think these images are pretty old. And before there was this NSF disease, nephroscope, something syndrome disease. It's a really bad disease where the kidneys fail because you inject gadolinium. It's very uncommon, but there was a big scare about this disease about 10 years ago because of some incidents. Okay, so let's do comparison. A few comparison between all those options in terms of the sequence, the type of spoiling, the transverse magnetization, the amount of contrast, and the SNR that you get from them. So balanced SFP, we don't do any spoiling. The transverse magnetization is retained from TR to TR. And the contrast that we get is approximately T2 over T1. It's not exactly, but it's a good rule of thumb. The SNR is high, but we have banding artifacts, right? These dark bands, if you have off resonance. Gradient echo, we use gradients to spoil the magnetization before the TR. The transverse magnetization is averaged across all possible off resonances, right? It's the average of this case. The contrast is still T1, T2 over T1, but again, it's kind of more washed out. Okay, it's yeah, it's a washed out version of it. And the SNR, I would say, is moderate. It's not high, it's not low, it's somewhere in between. Okay, because we still get this refocusing, we still retain some magnetization, but it's an average. And finally, the RF spoil gradient echo. You spoil using RF increments as well as gradient at the end of the TR. The transverse magnetization is effectively canceled. And so the contrast is pure T1 contrast. And the SNR is much, much lower because there's really no preservation. So whatever T1 recovery is giving you, that's what you end up seeing. Okay. All right, here's the quiz. Here are balanced SFP and RF spoiled post-contrast images. Which is the image on the left? RF spoiled post-gadolinium or balanced SFP?
Balanced SSFP.
That's right. Why?
Because I'm cheating because there's no gadolinium. And
well, here there is actually, this actually has gadolinium, and this is actually RF spoiled post-gadolinium. So this image over here.
oh, okay.
And so you can see the blood vessel being very bright, and also the edge, you know, are quite enhanced, and you can see the blood vessels, even the liver, are being enhanced. And so that's RF spoiled post-gadolinium. This is balanced SFP. You know, the way to look at it is, first of all, look for banding. I don't actually see much banding over here, to be honest. But what you do see is that wherever you have lots of water, free water, you have a very, very strong signal. So liquids have actually very bright signal in balanced SFP. Okay, so the fluid is very, very bright. It's actually T2 like, but just the fluid. The rest is kind of T2 over T1.
Don't you see a banding there?
I actually didn't see much bending.
Top, the whole top.
It could be, but it could also be the roll off of the, yeah, it could be.
Because the fat, the white fat turns black.
Yeah, but it's not conclusive. Actually, over here, maybe there's a bend. But it's hard to say if the coil, you know, or, you know, because here there's also darkness, right? It's also dark, so it could be the coil. Okay. So identify the images below. These have the same TR, the same TE, and the same flip angle. The only difference is that you do different spoiling. Okay, so what's the order? Take a look at a bit of hints here. You see the sinuses, you know, close to the air tissue. You may have something there. Look at here, contrast between gray and white matter. And then look at here. Any idea? Which image is this?
It's the balanced SSFP.
Yeah. What's the evidence?
There's the banding and it also has the highest contrast.
Highest SNR. I don't know about the highest contrast. I mean, it has okay contrast, but it's not great. You definitely see CSF. CSF fluid is bright, right? So fluid is bright on SFP. So the eyes are bright, for example. And the CSF is bright too. Which one is this?
RF spoiled.
Really?
Right. I don't know.
Which
I
has
mean,
more signal, this one or this one?
I mean, the second one looks like RF spoiled. I mean, lower
What?
SNR.
This one lower SNR than this one?
I mean, the contrast. Yeah, sorry.
Contrast is worse.
Yeah.
Well, contrast, yeah. So this is basically GRE, gradient echo, gradient spoiled, because the contrast is T1 over T2, T2 over T1, sorry. But gray matter and white matter have very similar T2 over T1 ratio. So that's a problem. And that's why the contrast is really flat here. It's very hard to see any difference. Okay, but the SNR is a little bit higher than this. This is RF spoiled also. And because it's RF spoiled, it's just T1 weighted. And because it's T1 weighted, then white matter and gray matter now have a difference. Because gray matter and white matter has a shorter T1 than gray matter. So it looks brighter. White matter looks brighter on T1. Fat also looks brighter.
You say why the second one has high SNR?
This one?
Yeah.
Yeah, this has a higher SNR than this one.
Why? Where do you see it?
You know, the image intensity overall is higher than this. Right, the noise is the same, right? They're scaled the same way. So here's the evidence. Eyes, you know, are white. So fluid, and of course banding. Here there's no banding, but the fluid is dark now because it averages, like you get all this averaging. So actually fluid is dark. By the way, so the averaging is not just magnitude, like SFP actually has phase in it. So that's why, you know, it actually cancels. And then the SNR is relatively higher. And then, yeah, over here, you see a much bigger difference than gray and white matter. So that's gradient, that's RF spoiled gradient echo. Okay. So now we looked at the first knob in these short sequences was pretty much the you know, the crushers, right? Here are some variation on these gradient echo-like sequences. Okay. By the way, when somebody says it's a gradient echo sequence, they either refer to SFP or gradient echo or gradient spoiled. Stop it. Gradient spoiled or RF spoiled. All of these are called gradient echo sequences because they don't have a spin echo. You know. So now what we could do is we could say, well, what if we change the flip angle? How does that affect my image contrast and my image, you know, SNR and all that stuff? Okay, let's take a look at that. And the question to you is, does increasing the flip angle increases the signal?
Well, isn't the answer always it depends?
Yes. That's true. It's a smart thing to say. Well, I mean, we've seen for saturation for the case where we have just a series of flip angles, right? That we did before this analysis. We had the Ernst angle, right? That maximized the signal at the particular, right? So obviously, the RF spoiled version, which is pretty much pure T1 weighted, behaves in the same way. Okay. The question is like how balanced SFP and also gradient echo behave. So the answer, yes, it's sometimes signal peaks at a specific angle. Okay. And here are just actually examples. So the green is RF spoiled. The red is gradient spoiled. And the blue is balanced SFP. So it really depends on many, like the contrast depends on, of course, the T1 and T2 for certain things. Let's look at, first of all, at the green one. RF spoiled is pretty much pure T1 weighted. And that actually behaves like the analysis that we did before with the Ernst angle. And that's actually where the Ernst angle happens. You see? That's exactly where the Ernst angle happens. It peaks over here. And that's the Ernst angle for those TR. And so you could actually see that the Ernst angle for muscle and blood, I mean, a little bit shifted here. So they're not exactly the same, but they're the order of just a few degrees, like 5 degrees, something like that. It's very small because you knock the magnetization so rapidly. And the level of signal is maybe 5% compared to the maximum magnetization that you can achieve. So it's very little, right? Now, what happens for gradient spoiled? Well, that actually keeps growing as you knock on the flip angle till it kind of peaks for a muscle at 20 degrees, and for blood actually peaks at 35 degrees. That's because their T1 and T2 are different. And then for SFP, you see that blood actually peaks at 50 degrees. And then for muscle, it peaks at 25. But if you actually pick the one that is the most, like 50 degrees, you see that now you have a really nice contrast between blood and muscle, which is a really good place to be when you're imaging the heart, for example. But the behavior is very, it's definitely for these steady state sequences, it's hard to say. It's like you need to do the analysis in order to do, to see what the maximum is. Yeah, so that's kind of like the area where, kind of like your signal peaks for these cases. Okay. And if you want to see, contrast, well, then you have to actually find what is the difference between this and this, and like at what angle, that change is maximized. Okay. So the question is, the best flip angle to use is found by maximizing the image SNR, 2, maximizing the contrast between certain tissues, or actually both. What do you think? It's actually an ill-posed question. How can you maximize both? Because obviously it's a Pareto optimal curve. Like you maximize one, that's probably not the maximum contrast. I mean, unless you're lucky. But you have to look at both in order to find the right trade-off. Right? Like it could be that, you have a really strong, contrast, let's say, between two tissues, let's say blood and muscle. But let's say at that point, muscle has no signal whatsoever. I mean, that doesn't make sense, right? Because we won't be able to distinguish muscle to like empty. right? So that is a problem. So you really want to have some kind of a nice trade-off between them, and people try to optimize that. And there's really not, there's no one great solution, but there's reasonable solutions. Okay, for example, here is the case where you want to maximize the signal between muscle and blood for SFP. And so for balanced SFP, I don't know, I mean, like here it's pretty good. I mean, here the blood is maximized and that is the difference. But then here, blood is a little bit lower, but the difference is higher. So that's maybe a better choice because now you get still pretty high blood. Muscle is a little bit low, but their contrast is more significant. Still, both of them are relatively high. Okay, so maybe that's a slightly better choice than this one. But both seems to be okay. So you'll see in cardiac images, quit it. In cardiac images, you often see in angles between 50 and 60. Very typical. Here are some other examples. This is RF spoiled. This is gradient spoiled. This is balanced SFP. And you vary the flip angle from 5, 10, 20, 30, 40, and 50. And the question is, which one would you pick? Right? I mean, first of all, I would say none are good for this. So I wouldn't use this for brain. None of them are good. So now I can say, okay, well, balance SFP. Let's look at the gradient angle. Which one? I mean, this has no contrast, but this one is really, really dark, right? So the contrast is good, but it's too dark. Maybe this one. Man, this one looks pretty good. I don't know, maybe this one. This one. Maybe this one. Here, the gray matter is really kind of nicely depicted. Okay, so maybe this one. I don't know. Who knows? I like this one now today. And this one is the best. Maybe. Okay, but obviously, or maybe this one. This one actually pretty good too. More like T2 here. So it really depends what you want to see. And thank you, Efrat. It depends. Okay, we're running out of timing. So I think I'll leave timing for Thursday. By the way, in terms of topic, we're going to finish this pretty soon. So we're going to talk about timing and then preparation sequences, and then we're going to move to SNR. Okay, talk about SNR on Thursday. Next week on Thursday, we have a special guest. My colleague, collaborator, and very good friend, Shrees Vasnawala. He's a pediatric radiologist. He actually is the head of pediatric radiology for the Children's Hospital at Lucille Packard Children's Hospital at Stanford. And he's going to come and talk for an hour and talk about the use of MR and describe different cases and how a radiologist actually looks at images. And I really, really strongly recommend not missing this one live, because it's really fascinating to see from a radiologist perspective, how they look at images and so on and so forth. So we'll have that next week on Thursday. So the plan is we're going to talk about timing next time, preparation sequences. We're going to cover SNR Thursday. And then Tuesday next week, we're going to continue talking maybe about SNR. We're going to talk a little bit more about 3D sequences and artifacts. And then on Thursday next week, we're going to have a radiologist talk, right? And then after that, we'll figure it out, right?
Can I share something, Mickey?
Sure.
I want to share that Mickey once told me that Shrees is the nicest radiologist he knows. I don't know if you remember that. Not to mention, yeah, it was a long time ago. Not to mention that Shrees is an international expert, so don't miss his lecture. That's it.
Thank you. All right. Well, I think that's it. So thank you very much for coming today. And yeah, hope you enjoy the popcorn. Bye, everyone.